Hi, I welcome you all to this enlightening session on a quantum mechanical phenomenon called as resonant tunneling and its application, the resonant tunneling diode. And taking you on this journey, it's Dr. Yunus Jerusha. There are two important perspectives to this tunneling phenomenon. One, according to classical mechanics, and the other due to quantum mechanics. According to classical mechanics, a particle impinging on a potential barrier with energy less than the barrier height will be reflected back, whereas a particle with an energy greater than the barrier height will climb over the potential barrier and be transmitted through. The second perspective, as I said, is due to quantum mechanics, where tunneling occurs when the particle is able to penetrate through a potential energy barrier that is higher in energy than the particle's kinetic energy. The act of tunneling decreases the wave amplitude due to reflection of the incident wave when it comes into contact with the barrier but does not affect the wave equation. This amazing property of microscopic particles plays an important role in explaining several physical phenomena including radioactive decay. Additionally, the principle of tunneling leads to the development of scanning tunneling microscope, or in short STM, which had a profound impact on the chemical, biological and material science research. So, what exactly is this resonant tunneling? First, let's talk about single barrier tunneling. In quantum tunneling, through a single barrier, the transmission coefficient or the tunneling probability is always less than 1 for the incoming particle energy less than the potential barrier height. Whereas resonant tunneling occurs for a potential profile with two barriers which are located close to each other. What is the need for this resonant tunneling diode? This device has intrinsic bistability and high-speed switching capability. It also consumes less power. It leaves a small device footprint and has increased functionality. Let us now look at the resonant tunneling diode. The potential profiles required for the resonant tunneling diode can be realized in semiconductor systems using heterojunctions, which utilize semiconductors of different types to create potential barriers or wells in the conduction band or the valence band. One type of RTD is formed as a single quantum well structure surrounded by very thin layer barriers. This structure is called as a double barrier structure. Carriers such as electrons and holes can only have discrete energy values inside the quantum well. When a voltage is applied across an RTD, a terahertz wave is emitted, which is why the energy value inside the quantum well is equal to that on the emitter side. As voltage is increased, the terahertz wave dies out and the energy value in the quantum well is outside the emitter side energy. Another feature seen in the RTD structures is the negative differential resistance on the application of a bias. Here we are going to look at how these resonant tunneling diodes are grown. The RTD structure can be grown by molecular beam epitaxy and in specific heteroepitaxy. Gallium arsenide and aluminum arsenide in particular are used to form this structure. Or you can have combinations of aluminum arsenide and indium gallium arsenide, or indium aluminum arsenide with indium gallium arsenide can be used. In heteroepitaxy, the substrate is a different chemical species to the depositing beam, but has a crystalline structure that geometrically mimics a new material crystal that now can be deposited on the target. Let us look at the structure and operation of this RTD. An RTD can be fabricated using many different types of semiconductor materials, such as the elemental semiconductor, which is a type 4 semiconductor, and also compound semiconductors such as the group 3, group 5, as well as the group 2 and group 6 semiconductor materials. Let us look at how this structure is actually formed. A typical structure is made up of using N-type gallium arsenide for the regions to the left and right of both barriers, intrinsic gallium arsenide for the weld region, and aluminium gallium arsenide for the barrier material. Let us see how this device works. Consider that the incident electrons have an energy E, and that at first all of the quasi-bound states E1, E2, E3 and so on up till En lie above E as shown in the picture. As E increases, tunneling will increase, reaching a peak when E is equal to E1. After that, a further increase in E will result in a decreasing current. This decrease of current with an increase of bias is called negative resistance. Further, peaks and values will occur as E approaches and then moves past the other quasi-bound states E2, E3 and so on. This is the IV characteristic curve which we obtain for the RTD, and at the peak is where we have resonance when the energy on the emitter side becomes equal to the energy of the quasi-bound state. Let us look at the operation and the IV characteristics of this RTD. We are going to look at it under two conditions: without bias and with bias. Without bias, the energy band diagram is as shown in A with no transmission. With bias, we have three distinct regions being formed. Let us look at the first region, which is the first positive resistance region moving from A to C in the curve which is depicted below. For low bias, as the bias increases, the first confined state between the potential barriers gets closer to the emitter Fermi level. Therefore, the current it carries increases. The second region is a negative resistance region from C to E. As bias increases further, the first confined states becomes lower in energy and gradually goes into the energy range of the band gap. So, the current it carries decreases. At this time, the second confined state is still too high above in energy to conduct any significant current. The third region is the second positive resistance region from E to F. This region is similar to the first region, as the second confined state becomes closer and closer to the source Fermi level. It carries more current, causing the total current to increase again. There are three types of RTDs. The first type of RTD is a 3-5 RTD. The 3,5 compound material systems are heterojunctions made up of various 3,5 compound semiconductors which are used to create the double or multiple potential barriers in the conduction band or valence band. They have reasonably high performance which has been realized. Such devices have not entered mainstream applications yet because the processing of group 3,5 materials is incompatible with silicon CMOS technology and the cost is high. Most of the semiconductor optoelectronics use 3,5 semiconductors, and so it is possible to combine 3,5 RTDs to make optoelectronic integrated circuits, abbreviated as OEICS, that use the negative differential resistance of the RTD to provide electrical gain for optoelectronic devices. Recently, the device-to-device variability in an RTD's current voltage characteristic has been used as a way to uniquely identify electronic devices in what is known as quantum confinement physical unclonable function, abbreviated to QCPUF. The second type of RTD is the silicon or silicon germanium RTD. Here, silicon or silicon germanium material systems have both hole tunneling and electron tunneling. Limited performance of the silicon or silicon germanium RTDs is due to the limited conduction band and valence band discontinuities between the silicon and silicon germanium alloys. Resonant tunneling of holes through silicon or silicon germanium heterojunctions was attempted first because of the typically relatively larger valence band discontinuity in these heterojunctions than the conduction band discontinuity for strained silicon germanium layers grown on silicon substrates. Negative differential resistance was only observed at low temperatures but not at room temperature. Resonant tunneling of electrons through silicon or silicon germanium heterojunctions was obtained later with a limited peak to valley current ratio of 1.2 at room temperature. The last type of RTD is the molecular RTD, which is small and therefore ultra-dense integrated circuits can be manufactured. It's a natural nanometer scale structure and vast quantities are available. In the structure shown below, the benzene ring chains form the conductive wires and the methylene group forms the electron barriers. The potential well is also very small. It is around 10 to 100 times smaller than the solid state RTDs. The various applications of the RTDs are listed here. They can be used as oscillators due to their negative differential resistance, the digital logic due to its bistability. It can also be used as inverters, memory cells, multi-valued logic, and for the realization of integration with silicon CMOS and silicon germanium heterojunction BJTs. In a very short time, RTDs are expected to replace transistors as a workhorse of ICs. Thanks a lot for your patient listening.